Okay. Hey everybody, my name is Konrad. I work on the Swift team at Apple. My focus is primarily concurrency and server use cases. You may remember me from my Java life, in which I worked on Akka or the reactive streams spec. And yeah, it's great to be back and working a little bit with the JVM. So I will introduce Swift a little bit, a quick show of hands. Who is aware of Swift? Who has used Swift? Okay, not so bad. So Swift is an open source language, works on many platforms, anywhere from Linux, Windows to embedded systems and firmware and anything between. Also WASM, which I don't have on the slide, but I just remembered. And it's a natively compiled language. It has an explicit goal to feel familiar to people coming from other ecosystems, including Java. It has it's memory safe by default and has pretty cool features like concurrency safety, verified at compile time as well. Since day one, Swift had an amazing C and Objective-C interop story, which is how it managed to slowly replace Objective-C on Apple platforms. And we since then added the amazing C++ interop, which is really cool, and today we're adding Java to that list. So, why do we even care about this? Primarily because of memory safety. So why do we care about memory safety? Well, memory safety vulnerabilities are the number one security vulnerability. So if we want to reduce those, it would be great to adopt memory-safe languages across the whole stack. And while Java is a good solution to that, Java's memory-safe, that's fine, but Java programs very often end up calling into native code at some point, and then you lose this safety. So it's our opinion that whenever you're writing native code, Swift should be the tool you should be using for that. So in order to facilitate that, we need to be supporting incremental adoption of Swift, and that also means interoperability with many languages and making it both easy and efficient to do that. My colleague Doug earlier on in the main track had a talk just about that, so a decade of moving more and more of an ecosystem into Swift and memory safety. So that was in the past already, but you can check the video. And where do we care about this? A great example is, of course, servers. So there's a lot of Java services out there, and there's an increasing number of native coding libraries written in Swift, and we would like to be able to call them both efficiently and nicely. The other situation is that is interesting for Java and native interop is Android. A common thing that happens is people want to have a shared library that is the core of their apps and maybe interesting algorithms, and they want to use it in the server, on their mobile apps, and anywhere really. So we think, again, Swift is a good language to do that. Goals and directions here. There's a small distinction on the primarily written in some language, where you can be primarily written in Swift, and maybe you need to call a Java library. And we do support that. We have some Swift macros and JNI wrappers, and you can kind of do that, but that's not what this talk is about. The second situation is when you have a primarily written in Java application, and you want to call into native code, as the previous talk gracefully explained with the new APIs that we just got with FFM. So this is what I will be talking about today. So Java and Swift, of course, have many differences, but you'll be surprised to find that they're actually a bit similar when you look deeper. Of course, Java is all about classes and objects, but it has primitives, and Valhalla is bringing value types to the JVM as well. Swift, on the other hand, has classes, but is very much focused on rich value types. So again, something that, the slogan of Valhalla, that codes like a class, works like an int, very much applies to Swift value types. Of course, both are memory managed, so we have a GC here in the JVM, and automatic reference counting. So yes, that is a difference, but for the most part of a developer's day, it's very similar user experience. And generics, of course, have a slight difference as well. So the JVM has type erasure at runtime, and Swift has generics, but with fully reified types. That will be an interesting thing to dig into. There's smaller differences as well, so Swift has errors which are values versus exceptions with stack traces, and the threading model, so virtual threads versus async await actors, are a bit different, but again, something we can work with. So, a typical application. You will have some Swift sources that either are from a library or it's your Swift sources, and you will have some Java sources that will want to use this native code. So we will build a dynamic library, depending on the platform you want to run it on. And here's the new things. We will have a tool that will generate Java sources that will make calling this native library easy. This is where we will be using the FMM APIs, the foreign function interfaces, to call down to this dynamic library. We will also have to generate a bit of Swift code, which is a bit unfortunate because with a plain C-style language, you wouldn't need to do that. And I will explain in depth why we have to do this bridging there. At the end of the day, you put it in a jar or you ship the dynamic library separately, and you can just call these functions. So we do have a tool that is called JExtract Swift. The name is very much inspired by the JExtract tool, which is something from the JDK that takes C header files and turns it into these Java wrappers that you can use to call these C functions. So our tool is very much inspired on that. Looks more or less like this, where instead of accepting C header files, we take Swift sources and again generate the Java code that it makes it possible and easy to call into these native functions. The tool is split up in a few phases. There's an analysis phase. So Swift is a very expressive language with, for example, you can have extensions on types located in other modules or sources. So we have to do a little bit of analysis to figure out which type has which methods. And later on, of course, versus the source generation step. Today we use the foreign function and memory APIs. We could have a source generation step that would use the legacy, JNI APIs for platforms that just don't have FFM yet. And we do generate these Swift funcs as well. So, how does it look like when we extract some source? Let's say we want to extract a Swift class. A Swift class is imported as this wrapper type, and we implement the Swift heap object. We use this primarily to know that, this object has to be reference counted, because we will try to do the right thing on the Java side as well as we import these types. When we extract a struct, we implement the Swift value, which again is a signal for us that, okay, we will be copying this Swift value around rather than reference counting it. Next, we will be generating all of these foreign function descriptors. The previous talk very much explained. So we generate those, so you don't have to write the function signatures by hand. And we finally generate the actual methods that Java developers will call, which kind of mirror the native shapes of the methods we'll be calling. An interesting thing here is, at the bottom one, you can see that these types can have other imported types. So I'm passing a mySwift struct in the Java side of things, and yes, this will be wrapping a Swift struct, and we can just call a collection of Swift libraries without doing like weird dances. We can just use them all, and it all fits together. So, I did say that we're using Swift sources. I feel that I have to explain that for Swift, it is typical to use Swift sources as package distribution mechanism. So when you publish a package, it's a Git repository, you get the sources, so we always have the sources available. But if you don't have the sources available, for example, you're using an operating system provided library or just closed source code, the same tool will actually work the same way, because Swift does have something alike header files, which is the Swift interface files, which are basically like Swift source files, but except having actual bodies and implementations, it's just cut out without the bodies. So the same tool works the same way with closed source or operating system provided libraries like this. Okay, let's dive in. And we will start from an interesting point, which is initializers, because they will lead us to some interesting discoveries I want to talk about today. So let's say I want to extract from this Swift source file. So it's an initializer, it takes a length, and it takes a capacity. The capacity is another value type. And I want to import that into Java. So of course we generate the function descriptor, as you can see here. It will return a Swift pointer, which is the initialized object. And we accept the length, and we accept the capacity. The capacity is a pointer to that struct. And, oh, wait, what's that? We didn't see that in the Swift signature. It's another parameter here, that is the Swift type. So somehow we will have to find out, at runtime, the Swift type metadata that we have to pass to this native function native initializer to be able to call it. So how can we find that? Luckily, we can just ask Swift to give us the type. So on the Java side, we generate a little call that will basically downcall into Swift using a well-known function name. And on the Swift side, it's very simple because we just write the type and we just return it. I'll talk about the details of these functions a bit later, but basically, I'm just returning the value out of Swift back into Java. And this should feel familiar because on the JVM we have class objects. And the type metadata is exactly that. It's the equivalent of a class object. It describes, hey, this type is this and that. The type is immortal, so I don't have to worry about like retaining it or anything like that. I can just return it like that. That's fine. We then store that on the Java side, and we're ready to call initializers directly. Very cool. So this way I can literally do a down call, and I get back a Swift instance that I now have a reference to in the Java side. What about value types, which is where I think we've spent most of the talk because they're more interesting. Value types are interesting because, of course, on the Swift side, they will be stack allocated. That's the reason you want to have value types. They can be stack allocated, and they're nice and efficient to pass around. So if we were to just return the same way as we did with the class, point to that, I would be pointing to the stack, which, it could very easily be not valid anymore as I use it in Java. So instead, what we do is we create a small allocation of the exact right size that the Swift initializer will fill in with the data of the struct. Now the question becomes, well, I don't know the size of that struct in Java. How do I find out? We have an analysis phase, so maybe I can do that. Maybe I can use the analysis to just do the math and figure out the size of the struct. We can do that. If that's an integer, that's 2 8 bytes, then, okay, I know that my Swift class is a class, that's a pointer, again 8 bytes, and then it's a struct. I have to look at that struct and recursively keep descending to figure out the size of that, and eventually I can find that out. Cool. I could also ask the Swift runtime to just tell me. So the Swift runtime, there's a Swift API called memory layout. You can give it a type and ask these kinds of questions. So you get the size, the stride. The stride is just the size plus any necessary padding to align it properly. So we could ask Swift as well. But before we do that, I want to explain why we have to do that. So what is the size of this struct? It's the same struct, but now the value and object types are generic. I know nothing about them. And more interestingly, well, they could be reference types, they could be value types. So the size of this struct at runtime really depends on how exactly it was used, and I don't know by looking at this type declaration at all. So I don't know how to generate this initializer. So another cool thing about that is, you may know if you've looked at Valhalla, which is we can produce tightly packed arrays and other structures using these kinds of mechanisms. But again, we have to know the exact type at runtime at the moment we're trying to initialize a thing. So how could we do that? We already have the type metadata, and okay, the type metadata doesn't actually have this information, but we can calculate a simple offset and jump to something called the value witness table. So the value witness table is something that contains a lot of interesting both functions and values that we'll be using to work with value types. Specifically, how to initialize, how to copy, how to destroy these values, and oh, great, we have the size and all the data we need to do our initial allocation for. How can I use that? So that is actually a C struct. So I can just describe it using the memory layout, struct layout. I literally just lay out, okay, this is this field, this is that field. I know this is an integer, these are addresses. And as I'm done with that, I can get a var handle at the appropriate offset for a given value witness table. Because I have that, I can get the size of any Swift metadata, Swift type metadata that I pass. So now we're able to not only just get, oh, I got the size, we can go a bit nicer and get the entire memory layout description based on this information. So I get the size, stride, or I calculate the padding, and I can return a struct layout that, it has the proper name that describes the Swift type name, and, well, today at least, it's going to look a little bit like this from the JVM's perspective. It's native memory layout, and it's a blob. At least it's the right size of blob, so we're happy because we can initialize and copy it using the value witness functions. But maybe we could do that a little bit better in the future. Today we don't have that metadata. We could do that, and then we could describe exactly, oh, I know this is an int, and this is an int, and we could do the absolutely correct metadata, and then even do direct accesses to the offsets rather than doing down calls. Okay, so we can check that. If I got that right, I can implement the initializer for the value type I talked before, because I just passed the value layout as we do the arena allocation, and then we initialize that using the initializer. As you can see, we can just print that on the Java side, and it always has the right amount of bytes we need to be passing around. It's really cool. We just taught Java to understand the layouts of native Swift objects. Now let's actually call some methods on things, and this will be also interesting. Let's have again, my struct, and I want to call a method called capacity on it. Capacity is another value type. So first thing first, I describe the function. The function is a member function, so we need to pass the self, as we call it in Swift. Let's say I pass it as the first parameter here, and then we describe the rest of the function. It's going to return, again, indirectly, because it's a value type, as we talked before in initializers. I do the dance with getting the value layout, allocate that, do the down call, and as I return, I wrap it again with the appropriate wrapper type. Now, how do I make this call? As any other non-C language would today, which is I have to generate a small func that will be calling using the C calling convention, and we make sure, using the cDecl attribute on the Swift side, that, okay, this has to use the C calling convention, and don't use features that C wouldn't understand, like generics and other things that Swift has. This function doesn't really do much except cast the things to the appropriate types and down call into the actual Swift function using the Swift convention, because it's Swift calling Swift. Now, in an ideal world, we wouldn't do any of that and just call directly. Right? This indirection costs us both build complexity, I have to generate these things, build times, I have to compile them, and of course performance, because there's yet another indirection in the way. So it would be cool if we could call directly. And maybe to explain even more so, why do we even need this indirection? Well, Swift actually has its own calling convention, and that's because it's optimized to patterns and invocations that it often does, and one of those optimizations in this ABI is that self must be passed in a register. So it's not like passed in a parameter, it must be passed in a register. But Swift has a stable ABI, so we can easily find out where we should be passing it. So the ABI is stable on some platforms, it's well described, you can check it out here. So specifically on ARM this register, on x86 in this one. Cool. So can we fix the JDK to use the Swift calling convention so I can get my magical dreamland version of directly calling? Yes and no. I believe the code is very well structured and we have an opportunity to do that. It would be here in the call arranger of a specific platform, or maybe the calling sequence builder, which would, we would maybe tell it, hey, this parameter is special. So that's the good news. The bad news is these types are JDK internal, so that's not something we did today. But it's certainly a possibility. And other runtimes like the .NET runtime in version 9 have actually explored that a bit, and that's a PR that implements parts of Swift calling convention. Again, to be able to call directly rather than from some C shims. And finally, a little bit of object lifetime discussion, because object lifetimes and memory safety is kind of the core of our goal here, right? We want to have this integration, have it nice and safe. So how do we do that? But before I say how, I need to explain what really destroying a value means in Swiftland, because it's actually a little bit different than on the JVM. So again, value types. I have a value type called container. It contains a number, cool, primitive, a person, and the person is a reference type. So if I create this container and then assign nil to it, because we're reference counted, the way Swift works, this will be then, this will call destroy on this value type from our good friend, the value witness table. This will then go through all the fields and call destroy on them, or if it's a reference type, eventually just release a retain count release on it. If that hits 0, we have to run the initializer. And we're going to run the initializer right now and not at some later point like it would be with finalizers on the JVM. So developers expect this to work like this. So what do we do to make it work like this? We actually got inspired from the Arenas API, and we offer something called a Swift Arena in the support library that comes with all of this. And yes, it's a segment allocator, same as Arenas in the JDK, but we also, when we do initializers or return types, we register them with the Swift Arena. Now, we register them, of course, to manage their lifetimes. So as I have registered, for example, in a Swift Arena of confined style, which is again inspired by the OpenJDK Arena, at the end of the scope, we will call destroy on all the types that were registered with it. Again, the destroy will do the right thing here. The same pattern applies for reference types. You can just register them, create them in the scope, and we will just reference count down on them. Today, if we don't reach reference count 0 here, we assert. But I think you could totally see valid use cases for maybe you want to assert if it didn't get released and destroyed at the end of the scope, or maybe you do actually want to just keep this style for maintaining reference counting. So this is something we can do. And we also try to guard against programmer errors. So on the Java side, you could make a mistake and unsafely escape the value created during this scope, and you try to escape it outside of it. So of course, after the scope, this value would have been destroyed. You would be pointing its stale memory. So on the Java side, as we do the destroys, we mark them so we don't try to down call into memory that was already deallocated. Again, all in the name of safety, so we don't do bad things here. We do have an auto arena as well, again inspired by the OpenJDK, where we use phantom references and a cleaner thread to clean up these objects eventually. I think it's great for prototyping if you want to show, either a Java or Swift developer, hey, please give this a go. I think that's a good one to start, and there may be other situations where you want to rely just on the GC to release things as well. Of course, it's less predictable then. So for Swift developers, this would be can be a bit surprising. As you can see, this is a very deep integration. We're not just saying, hey, you can call simple functions. No, we're shooting for integration of both a programming model, trying to ensure its safety, as well as making it a pleasant thing to use. And with the end goal of being able to import really most, if not all, Swift code we have laying around. So if you walk away from this talk, I'd like you to remember one thing, that our goal is here to have memory safety all the way. We don't have to lose memory safety as we cross into native land. And if we collaborate from both sides, the JVM and the native language, enforcing each other's patterns, then we can pull that off. Swift and the FMM APIs really work well together. I didn't show super crazy advanced cases, but we can integrate them very deeply, even with more generics and use cases I didn't show today. And value types are the core of Swift, and we can actually deal with them pretty well in Java, which has been great. So there's ongoing work on JExtract Swift. If you're interested in integration between languages like that, please let us know. And what are the upcoming next steps we can look into? Of course, performance. If you're interested in performance, that's a never-ending story here, of course. We'd like to challenge a little bit of the generics because we want to support optionals and conductions, and then we will have to handle generics as well. Swift closures and passing a closure to a Swift function and then calling that on the Swift side, we can implement using upcalls into the JVM as well, and express Swift closures as functional interfaces. And there's other calling convention differences, for example, for errors or async code. And last but not least, build tool integrations. So that's all I had. If you have questions, please check me outside later on. And thank you very much.